making them power efficient, building their own backup generator technology, their own construction standards.
18 exaflops, and we're again at 700 exahashes. We're actually getting ready to approach the zettascale there.
Clearly, liquid cooling was all over the show floor this year. If you had a very narrow view, you might think you were at an auto show.
The HPC sites around the world are increasingly looking to have the traditional CPU, GPU-based supercomputing with a quantum computer accelerator attached to it.
Welcome to the Orion X Download Podcast. Join Shaheen Khan, the Orion X analysts, and special guests as they discuss and simplify the big ideas and technology that are changing the world. Thank you for being with us.
Hi, everybody. Welcome to another episode of the Orion X Download Podcast. Here with me is everybody in Orion X analyst group, Adrian Cockcroft. He and I have had a couple of podcasts in the past. Stephen Perno, who is here from Asia and also ready to talk about the latest CryptoSuper500 list, and Chris Krull, who joined us a few months ago and brings a background in storage and systems and software. So what brings us together here is the Supercomputing 24 conference that was held in Atlanta last week. It's a conference that has grown over the many years, starting with deep high-performance computing, scientific engineering, and over time has become a lot more of a general purpose, significant to IT departments, including AI. So this past week, we had 18,000 attendees in Atlanta. That was a 25% improvement from the previous year. About 500 exhibitors from 29 countries. That was a 30% improvement from last year. The exhibit area itself appeared to be a good 50% larger than the previous year. So it's starting to be a major show. Chris and I were there in person. Adrian and Steve were planning to be there in person, but other things came up, so they had to go through the digital experience is the word, I think. So any immediate reactions, Chris, since you were there as well?
Sure. So this is my first time back at the show in 8 years, and it was really fun to see the growth. It was great to catch up with colleagues from the past, and it was interesting, perhaps not surprising, that some of the same challenges that we've always had to face, bandwidth and bottlenecks, for example, still exist.
So was it like a soap opera that it's still exactly like you left it off?
Yeah, some of the branding has changed along the way, but the players are by and large still the same fun crew.
Right. Now, Adrian, for the past 2-3 years, since we've been attending it together, you've written an article after the show. It's been featured in Inside HPC, and you usually complement that with a longer Medium article, and that includes some predictions. Do you want to go over the predictions from last year and also your general perspective on the show?
Sure. Yeah, it was good to go the last 2 years. As Chris said, met a whole bunch of old friends and sort of really got back into the industry. I had previously been about 20 years before when I was actually working for Shaheen. We were both at the Sun together doing HPC. And then as I sort of was looking at what was happening, I tried to track things like what's going on in computer architecture. And 2 years ago, there was a lot about CXL and a lot of, and also the sort of the transition into cloud. There was probably the two main areas where I was interested. And a couple of things from last year. One was that there was a new entrant in the top 500 list from Azure with the Eagle system that they put together in a few days with a few people and got it was a third place result last year. And it's now been leapfrogged this year. And one of the things I thought would happen was, since it didn't take very long, I thought more cloud providers would actually go out and run their own HPL results on large cloud environments, but that didn't happen. So maybe I was ahead of myself, or maybe they're just too busy trying to get them to run AI to run a Limpac result on it. Maybe you can just talk a little bit about what changed in the top 10.
Yeah, there were 3 new systems in the top 10, and Microsoft gets great kudos for participating, and they now have 5 or 6 systems on the top 500. Obviously, they have massive infrastructure. If they really wanted to run the benchmarks on more compartmentalized zones that they have, they could. But it is wonderful that they are participating and they're providing the information. The three new systems obviously include the new number one from Lawrence Livermore National Laboratory, the El Capitan system that is an HPE AMD system, and it broke the 1.5 exaflops performance mark. It came in at 1.74 exaflops, which is quite massive. One of the things to remember is that these exaflop systems are running that much performance on one application. It's not just an aggregate level of performance available, which the cloud vendors can do in abundance, but to harness all of that towards one application in 64 bits is not common.
Yeah, the thing though is these big data centers, the big supercomputer systems from Cray HP that are built at the national labs, they take years to plan, to build, to get working, and they're rolling out gradually. The cloud environment, we've already got all the hardware sitting there. The question is, can you get enough of it together in one place for long enough to actually run the system? So it's a very different environment from a software point of view. You don't have all of the layers of software that the labs have built out for running all the workloads that come with the labs, all of the traditional supercomputing codes. But if you just want to run one code, then you can do that in a few days on a cloud provider. You just have to allocate enough hardware to do it at one time. So the amount of effort you put in is dramatically lower to get a number. And maybe we'll see some more numbers come out from other providers or from Azure getting an update, particularly as the Eagle system was NVIDIA H100s, and we're starting to see NVIDIA shipping H200s into real environments, and they're just starting to ship the first B200 systems, Blackwell systems. So I suspect that somebody will come up with a Blackwell-based number at some point.
Yeah, one thing to point out, my take is that the national labs aren't just looking to provide compute capacity to their users. They're also trying to preserve the know-how and the ability to build these systems, and also to drive the future architectures for HPC. And that puts them in a position where they are ahead of the market in some ways. They have to focus on technology that isn't available. That's not common across government agencies. Some agencies go for what's available today, off the shelf, off they go, and they are much faster in deploying and running it, even if it is on-prem. I expect that all of them will morph into a hybrid situation where they take advantage of public clouds that are compartmentalized and zoned off for them with all the proper securities, while also pursuing on-prem. And that, I think, is an important distinction for what DOE is doing.
Yeah, and the other sort of prediction we were making from looking at over the last couple of years was that the next generation of hardware is going to be more custom. And I don't think we've seen that happen yet. We're still looking at either NVIDIA AMI or Intel-based GPU acceleration with the HP Cray architecture for those systems. We have Fugaku being the only custom design system right now. And the team that built Fugaku seemed to be doing a lot of work with AWS recently rather than building a new system. So there's something happening in that environment where they seem to be porting codes over to AWS, porting their software environment over to run on the cloud rather than, it seems, building a next generation machine. I'm not sure if there was any updates from that group.
No, the only one I noticed was there's some discussion with AMD to use their CPU with AMD GPU, something like that. The news articles basically whipped it up into, is AMD going to have a specialized chip? But the concept is compatible with the emergence of chiplets and tiles, where you can imagine different IP mixing and matching on the same die. So let's talk about benchmarks a little bit. As we kind of alluded to with high performance LIMPAC, there was also the Green 500 that is occupied mostly with Eviden with the top two spots, and then HPE and Lenovo scattered around. Those are the three vendors that have put a lot of effort into direct liquid chip cooling, and we'll talk about that when we get to liquid cooling. But the star of the show for us today is CryptoSuper500. Steve, you've been working on that for several years and putting out reports every 6 months religiously. There's a vast body of information that's gathering there that's really highly useful in tracking the world of crypto. Do you want to do a quick intro on what the list is and what the new one is bringing to the table?
Yes, thanks, Shaheen. And you've talked about the frequency. We've been doing it for 6 years now. So this is the 13th list, and we always do one in conjunction with the Supercomputing show in November, and another one we do 6 months away in conjunction with the European conference, ISC. And what we find, of course, has been a very enormous growth in the hash rate, which is the measure of the collective mining of the Bitcoin network. What's happening is a cryptographic lottery, a winner-take-all lottery is being solved every 10 minutes, every block. And now the hash rate for that is reached 700 exahashes per second. So Bitcoin computation has been in the exa scale for a long, long time. Now it's not directly comparable to 64-bit work. In fact, it's integer work, mostly 32-bit integer. But a hash is not a single integer calculation. It's a group of order a dozen calculations, including shifts and moduli and integer adds, that kind of thing. So it's not completely trivial. That network is the world's largest decentralized supercomputer, and it consists of millions and millions of nodes. And these are called mining rigs in the industry, but they're based around custom ASICs that implement SHA-256-bit hashing protocol, version of SHA-2. And the individual nodes are now running at up to 400 terahashes a second for an individual node. And there are some coming out before the end of the year, supposedly, that are above 800 terahashes. And speaking of liquid cooling, the ones at the high end are now all being water cooled or liquid cooled because they're drawing power at the scale of 5 kilowatts and even 7 kilowatts. And the one I just mentioned, coming out at 860 terahashes, is going to be at 11 kilowatts for a single node. Now, we can do a very rough comparison of this to the top 500 systems and lists, not directly in terms of flops and hashes, but just thinking about chips and how many ASICs are required and how much power is being consumed and what the cost of the systems is. So if we look at El Capitan at 1.7 exaflops, and then we look at the collective of the entire top 500 list, that's about 10 times that at 18 exaflops. And we're again at 700 exahashes. We're actually getting ready to approach the zettascale there. The number of cores in El Capitan is 11 million. And the number of ASICs that need to be deployed to meet the 700 exahash hash rate, if you did it all from one relatively high-end system, would be nearly 2 million ASICs. And those ASICs are 12-way multi-threaded. They're in 5-nanometer technology. And you'd require 150,000 cabinets for that globally decentralized supercomputer where they're all collectively working on that same problem, racing to win that Bitcoin subsidy reward. Collectively, that would be 13 gigawatts electrical power being continuously drawn. The Cambridge Center for Alternative Finance estimates the network at 19 gigawatts. So we're of that order of magnitude. I've approximated it all by a single system for ease of calculation, but we know that there's a lot of older hardware in there. So there are probably 3 to 5 million collective nodes that are running the network. And the output now is $16 billion of annual economic value of Bitcoin, with a block subsidy of 3 1/8 Bitcoin every 10-minute block, and with the current price in the low 90,000 zone. We've been running the list, as I said, for 6 years, and when we started out, there were 5 or 6 of the proof-of-work coins that we monitored, and only proof-of-work coins matter because they're the only ones that are using a lot of supercomputing power. So they're the only ones that matter for this list that was inspired by the top 500 list. So now the second one is Dogecoin. It's good for about $1 billion of value, and it all adds up to about 17 billion economic. And the electricity input is greener than average. They're getting close to about 60% of green and no carbon, including nuclear sources. So I'll hand it over with that. If there are any questions, be happy to answer.
Yeah, I think if you called it federated supercomputing, it'd be where the HPC world wants to go. And Control IQ, CIQ announced their fuzzball federated computing, which really is about using resources from disparate locations and technologies towards one application with all the data management and security and such on the radar. But it's interesting that the Bitcoin network is providing that level of power.
I will add one interesting fact, which is also relevant to the way the top 500 list has been tracking, how much computing power we have coming out of Europe and Japan, how many are on the top 10 list and further down the list, and out of the US, of course, and in the past, China. And in the same way that China has dropped off the top 500 list, it's dropped off the CryptoSuper500 list conceptually. We track the hash rate as well as we can by pools. Pools, it's a little hard to tie them down to nations, although they have headquarters. They're pulling in hash rate from everywhere. But the most interesting thing was when China cracked down 3 years ago on mining for a couple of reasons, energy conservation and their own digital currency that they were introducing, that a huge amount of the Bitcoin mining and hash rate shifted to North America, and in particular, venture capital funded startups. So there are over a dozen that trade publicly, and they're now responsible for 1/4 of all Bitcoin mining. So that's been a big shift towards the US.
Another interesting thing is with the emergence of AI and all the energy that it uses, it sounds to me like Bitcoin has got a little off the hook in terms of being blamed for the energy use and, according to some, energy waste. And of course, they also refer to AI energy use as a waste, some of those guys.
Yeah, that actually brings up the whole liquid cooling and these very hot systems that are coming out now. We saw earlier this year that NVIDIA announced its Blackwell generation of GPUs, and including a rack-based configuration called the NVL72 that has 72 of them in a rack. But the interesting thing is the rack is water-cooled up to 120 kilowatts. That is expected to roll out in pretty high volume, given if you just look at the amount of business that's going to NVIDIA right now and the growth rates they have. We're expecting to see a lot of those. And last week at SC, there was an announcement from Dell and CoreWeave. I think Dell shipment to CoreWeave, the first shipment of that rack. So that's been interesting to see. Water cooling is an old mainframe thing, or maybe a few supercomputers deal with it, but it's now moving to mainstream.
Yeah, Chris, you want to chime in on liquid cooling? I saw your email on that.
Yeah. Clearly, liquid cooling was all over the show floor this year. If you had a very narrow view, you might think you were at an auto show with the likes of Valvoline having a large booth, and Castrol had a presence, and some others that I'm forgetting.
Shell.
But
yeah, was it Cray was a plumber or something? Was that it was an old quote?
Yeah, clearly the plumbing union should be an offshoot of HPC for sure. But there were several vendors there touting single phase, dual phase immersion cooling. And there's actually, I spent some time chatting with the folks at Chilldyne, which uses a negative pressure solution such that if a leak occurs or a line gets severed, because they're using negative pressure to move the fluid around, the leak does not become an issue.
So cooling sucks.
Yeah, exactly. Yeah. But immersion cooling, and clearly those of us who have been at Cray for a while have a background with beginning back with the Cray 2 system. But you couldn't escape the whole liquid cooling proposition at SC this year.
I had a similar impression. It was very much front and center this time, more so than previous years. Liquid cooling has been at this show for many years now. And this year it was just a lot more present, obviously driven by AI, and also a visible conversation about immersion cooling, not just direct liquid cooling. And immersion advocates believe that that's the way to go ultimately, and it is going to be the most efficient way to take heat out. But of course, it has complexities, operational complexity, leaking, like you mentioned. This whole liquid cooling is bringing chemistry and biology and fluid dynamics into electronics. It's very much the kind of stuff that this crowd simulates for their day jobs, and now they can do the whole system.
So just to clarify that, so I'd say direct liquid cooling is you have a heat sink and you're just running water through it typically. Whereas immersion cooling, you're actually bathing the chips directly in a liquid, which hopefully is not water, it's some more oily thing that's not going to mess up the silicon, but it's actually directly contacting the silicon.
That's right. So you want to take heat away from silicon. The one way to do it is that you have a cold plate right on top of it that takes the heat away from the chip to the cold plate, and then you put water in contact with that cold plate. And then the water or the fluid runs through that, and that can be single phase or dual phase. The second one, as you mentioned, is that you bathe the whole thing and just dunk it into that fluid. As you also mentioned, if it is water-based, then it has issues. Water is a very good thermal conductor, but you run the risk of generating mold and corrosion and things like that. So if you...
Water's a fairly good electrical conductor. That's the problem.
Exactly.
Right. You want something that's going to be electrically not going to mess with you. You've got these incredibly small transistors all switching at gigahertz. If there's something around them that messes with that, it's going to stop the chip from working and corrode it and things like that. So, yeah, so they've got to have some interesting chemicals, but then the whole technology of how you get the right amount of fluid in and out of the chip, or the pressure, like this idea of basically pulling the fluid through instead of pushing it, sounds like a good idea. But then if you've got a leak, you've got air getting in, so you have to kind of deal with that somehow.
Now, if you're doing direct liquid cooling, the fluid that runs through the pipes, that can be water-based. But then, as you said, if you want to prevent it from conducting or prevent it from developing biological, molding and stuff inside, then you have to create solutions, and that puts you into the synthetic world. So generally, for immersion, you need a dielectric fluid, which means it conducts heat but not electricity. And Cray 2, as Chris, you were pointing out to some of the attendees, had that a few decades ago.
Right, but the floor inert that Cray was using back in the day from 3M clearly has some toxicity issues that won't play today. So they've moved on from that fluid.
We saw Valvoline and Gates on the show floor, and they are two names you would not expect to see at a supercomputer show as brands. Gates make rubber hoses that you find in cars, and Valvoline, they're an oil company for lubrication oil, but they've obviously branched out into this area.
Yeah, and Gates was also touting an electrical pump that they pointed out the smaller form factor and more efficient energy usage. So they're clearly going into this space wanting to gain some share. So it was quite interesting chatting with those folks. And then with Valvoline, we had a couple of conversations there. And, when I think of Valvoline, I think motor oil, right? And when I think motor oil, I think lubrication. But their material science guy was very quick to point out that these types of fluids provide more than just lubrication. There's cooling, which of course is the big headline topic here at the SC show.
There's a lot more cooling going on now with electric cars with battery and motor cooling, with these sort of 500 to 1,000 horsepower electric cars. So I think the whole area of oil-based, a lot of them are oil cooling. They typically use oil cooling in the motors and water cooling or glycol or whatever for the batteries. And that market has expanded enormously. So the whole idea that you're cooling electrical equipment is a very big market that's growing in multiple domains.
Yeah, those are the two categories that were often mentioned, glycol-based and oil-based. Mm-hmm. And Chris, as you were mentioning, in addition to lubrication, there's cooling, cleaning, and that includes prevention of contamination, sealing, and then, of course, protection against corrosion. So you add all of those five together. The idea was that in this case, cooling is more important perhaps than lubrication, but it's an area that, like you said, Adrian, they are using quite a lot in high-end cars, and they splash oil on top of the cylinder to cool it as it goes down. Otherwise, it would expand too much. So it's all of highly precise chemistry and material science going on. But you combine all of that, you get longer life for the chip because they're running at a more stable temperature. They made a really big deal about thermal management and thermal gradient management and variation in temperature. So if you keep it at a relatively constant range and manage to cool it constantly, that expands the life of the chip. It also, of course, is more environmentally friendly, and it actually saves you money. So those were the big benefits of liquid cooling, even though it is in fact higher cost and more complicated to run.
Yeah, and there's a direct-to-chip cooling company that I chatted with called JetCool, which is recently, I think they announced it just a few days before the show. was acquired by Flex, the large electronics manufacturer. And they had a solution that was trying to put the liquid on the hotspots generated by the chip, as opposed to just blanketing. So I thought that was a pretty interesting. And I also thought the acquisition of the company by Flex spoke about the role that liquid cooling is playing in probably not just HPC, but in data centers in general.
We're starting to see chiplet-based systems move into the mainstream as well.
Yeah.
One of the problems that NVIDIA Blackwell had as it was rolling out, the GPU is built out of two chips connected together along one side with a 10 terabyte, I forget which, but a ridiculously large high-speed connection that goes over the chiplet substrate. And they had some thermal expansion issues where as it heated up and cooled down, the alignment was getting out, and so they had to spin the chips, and that was caused a slight delay in getting the Blackwell chips out. So it's clear that if you've got lots of different chips all glued together or basically mounted on a substrate, that if you've got thermal expansion issues and the temperature of the chip is varying a lot, those chips are going to either break or go out of alignment more often.
Now, that's a problem that people like Cerebras that do the whole wafer scale chip see in abundance, and it's heat distribution on the chip, but thermal expansion as a result, and the structural stability of the chip as a result. It can get more brittle.
Yeah.
A lot of really cool problems to solve that they seem to have solved. Cerebras has an engine block, as they call it, that has it all contained in like heavy, it's a pretty small one, size of like a, 15, 16 inch, about a foot tall, and really block looking thing with thick metal in there that does all the stability and the cooling.
Yeah, that's like a dinner plate sized chip, complete wafer. And if different parts of that wafer were getting much hotter than the other parts, you'd be generating thermal stresses across the chip that could eventually break it up. So they have to maintain the temperature evenly across the whole chip, not just think about performance.
That's right. It's 4 trillion transistors and 72 square inches.
Yeah, it's really impressive. And the technology they're in is actually a generation or two behind the latest NVIDIA, sort of the latest TSMC. So they've got some interesting headroom as they scale that up as well.
They do. So the show also has had a quantum village for the past few years, and I managed to swing through it. Steve, I know you have the proper background scientifically, engineeringly, and also tracking it. Maybe you want to make some comments about it, and then I'll chime in with what I saw.
I think quantum computing in general is the road that we're on that is taking some time, some number of years to get to realization. It is not something that's hit as a whirlwind the way that AI and deep learning have. But what we're doing is we're seeing steady increases in qubit counts up to of order 1,000 qubits. But the big challenge has been the problem with noise in the system and maintaining coherence across the qubits for a sufficiently long time to do useful computation. And really useful computation like Shor's algorithm, if you want to crack all of the public-private key pairs that are used not only in Bitcoin wallets, but in the whole financial system, is going to require hundreds of thousands of logical qubits. And here we are at of order 1,000 qubits, and you typically have needed something like 100 physical qubits in order to produce one logical qubit. Now, there have been a couple of groups that have recently announced headway in handling the noise in more innovative ways, and so that ratio is dropping. But we're on a road that has many different kinds of underlying technology that has ranged from superconducting technology to trapped ions to neutral atoms to optical methods. Which ones am I forgetting, Shaheen? There are a couple more, but those are the principal ones.
Silicon spin, maybe.
Silicon spin is, and the typical ones that are leading have been the very low temperature superconducting loops and require extensive refrigeration, ranging up to the neutral atoms, which allow you to be less severe with some of the cooling technology. And then perhaps the most promising for room temperature are the optical
Photonics
techniques. Photonics is one of the companies in the UK, Orca, and there are a number of others. So photonics in general. So I think where we are is something that's received a huge amount of venture capital, investment capital into the industry on a very great promise and waiting for returns. And we know that the application domains that seem most promising are in studying very high dimensional systems in order to solve optimization problems. And this has some overlap with AI. And then certainly areas like quantum chemistry, modeling materials, and nanotechnology, and then modeling for drug development, drug design, or other chemical design.
Exactly. What I saw was very consistent with what you said. The applications are optimization, and that includes parameter optimization for HPC applications, not just the application itself. And then the application itself is really obviously quantum physics, quantum chemistry, because, well, they're already quantum. In terms of deployments, the HPC sites around the world are increasingly looking to have a hybrid presence with the traditional CPU, GPU-based supercomputing with a quantum computer accelerator attached to it. And you see various sites go that way. The big sites have already done that. The national labs already have test beds. Companies like IQM, based out of Finland and Europe in general, have sold upwards of 30 systems. These are superconducting systems. And then Orcom mentioned that they've sold 10 systems around the world. Obviously, IonQ, Quantinium, and then you get IBM and what Microsoft and Google are doing. And then Quera with the neutral atom with a really good error correction and coherence times. So lots and lots of progress. And every one of these milestones is pretty significant from a scientific engineering standpoint, but overall appears to be still have some distance to go before you can actually incorporate them into actual productions. It still seems to be solving problems that are too simplified to be of much use.
We're also seeing sort of quantum-inspired algorithms running on GPUs, different software approaches. So it's not maybe leading us into ultimately running those algorithms on quantum computers, but at least getting some benefits from an intermediate stage.
This is a lot of their business approaches, the ability to run quantum algorithms on compute-dense, GPU-dense systems, and then hybrid computation. And more, it seems like that hybrid computation is moving in the direction of AI, that they're focusing more and more on, how they may contribute to solving AI problems, particularly on the side of optimizing in a very high dimensional space. I have a question for you, Shaheen, in terms of what we think the characteristic timescale in Moore's law sense is for quantum computing and for AI. In the AI space, people talk a lot about doubling capabilities, something like every 6 months. What do we think it's like in the quantum space? What is the timescale?
Well, if you look at the roadmaps that have been published, and IBM gets credit for publishing the roadmap and pretty much hitting it more or less as planned. And that has compelled others to publish their roadmap. And the roadmaps start getting really interesting in the 2030, 2033 timeframe. That's when you get enough logical qubits with enough error correction, enough resilience that you can say, okay, I think I can run some real application by then. But of course, that's still, 6 to 10 years out, and we'll see. If they hit that, I think that would be really interesting and cool. The other thing I want to mention is that many of these quantum computers are really quantum experiments with parameters that can be set here and there. They're not fully programmable quite yet, but we need to get to that point. And the software infrastructure is being built in parallel and even ahead of the actual computers. And as Adrian, you mentioned, right now the main beneficiary of that is really the GPUs, because you need to get to quantum advantage before the quantum computer just leaves everybody else in the dust for the codes that it is good at. Okay, so let's move to AI versus HPC. My impression was I didn't actually see an overwhelming amount of AI in this conference, but many people I talked to did, and they thought it was like everywhere. So let's talk a little bit about AI versus HPC and how we see it in terms of different market segments or different application areas.
I would concur that there was a large AI presence. When you walked around the show floor, that you could see the initials AI all over the place. But when you talk to people, AI didn't seem to be front and center of the overall conversation. And Shaheen, you and I had a conversation where we basically landed that AI is an application in the big pool, the big umbrella that is HPC. AI uses large-scale systems, HPC, same thing. We've seen the growth of systems throughout the history of computing to take on these large-scale algorithms and the massive amount of data and language processing that they're trying to do. That was the lens that I viewed it, but others saw it. This is a very great show to have a conversation about the path to, AGI. So maybe it's just your perspective on and what you're looking for.
Well, I think if you see HPC as simulation of natural phenomena, then you say, well, that's not what AI is right now. It's like generating pictures and text. But if you see it as a discipline that is computationally intensive, mathematically driven, a lot of matrix multiplies, then it sounds a lot more like HPC.
Well, I'm going to quibble a little bit with your statement there. When you look at what AI does, right, it's processing large amounts of language and speech, and what is that? But it's a product of our brain, as Adrian points out, is sort of a natural phenomenon in and of itself. So
it looks natural to me.
At least most of ours. I don't know. Got to question sometimes, but
fair point.
So but at the end of the day, it's an application that's trying to make use of large compute resources, and therefore I see it as fitting under the HPC umbrella.
Well, the big thing that comes out of the AI versus HPC discussion is numerical precision. The perspective that HPC traditionally requires 64-bit precision, but AI, having started with 64, going to 32, 16, 8, 4, and the joke is you kind of get to FP1, which is like plus infinity, minus infinity, and you're good, or 0 to 1 and good, even an integer. So what gives? And I think the counter idea is that stuff can also be used by HPC applications, and HPC has had integer and low precision workloads, most prominently in bioinformatics and in seismic processing and signal processing. So precision sort of becomes a bit of a red herring.
Well, yeah, and I think the two of you in a separate conversation that we were having were making the point that we will see the need for more precision in AI as time goes on. People might not see it now, but
the press briefing that they had at SC around the top 500 also included an AI update and a quantum update and liquid cooling update. They talked about that 64-bit may very well come back and be important in AI.
Yeah.
And Gen AI isn't the end-all be-all. There will be other advances that need to be made in AI. And as they do, it may very well become necessary.
Yeah.
My personal view is that life is generally 3D partial differential equations that you linearize and you have matrix algebra help you solve it. And that's why nature has so many matrix multiplies in it.
I was just going to make the point that there have been a couple of topics that we've touched on that lead us to optical, right?
Right. One final comment on AI before we go to optical, and that is the marked difference between training and inference. Basically, training being one application taking advantage of 20,000 GPUs, let's say,
yeah.
Whereas inference being 20,000 users taking advantage of, let's say, fewer GPUs.
Mm-hmm.
And the dynamics and the economics and the TCO analysis and capacity planning is all highly, highly different. And because you train once and infer a lot of the new players are focusing on inference as a market segment that they have a shot at, and they don't have to directly compete with NVIDIA.
Sure. And as I was chatting with folks, I was trying to poke at, I was jokingly referring to as MLM and SLM, right? We have large language models, and why not medium and small?
Indeed.
Going after certain disciplines. And clearly we see it emerging in different applications that we all use on a daily basis. But I think in the scientific arena, there's a lot of value to be had in being very specialized.
That's very true. And the other thing is that all these big players are really pursuing AGI, artificial general intelligence. And they're not trying to get one task done really well. For those who really are working on a much narrower scope of what they're trying to do, a small language model will very well be sufficient. And if you have clean, good quality data, that can reduce the size further.
Yeah.
The other thing is, it's not a single model that you put your question into or your input into and get an answer. We're now seeing a lot more agent-based or planning-based things. So the first thing that when you give the question, it says, okay, I'm going to break that question down into a plan. I'm going to farm that plan out to a whole bunch of specialized agents, and then you're going to gather that up and have what looks more like a human thought process of I got all these different things I'm thinking about, but I don't actually answer the question until I've thought about it for a bit.
Mm-hmm.
So we're starting to see more architectures that look like that, where the individual models are actually smaller and they are relatively cheaper to run and relatively fast to respond, rather than trying to make it one huge model which gets everything right in one go. So in some sense, a bit like more breaking it down into micro models, or it's just a monolithic model. That's a trend that seems to be happening at the moment.
Also scarier. When AI can do planning, that's the beginning of a problem. People worry about AI taking over the world. The root cause of that is the ability to plan. So if you can plan, you can then do things that nobody expected you to do.
Well, they're already doing that,
Right.
taking over bits of the world, I guess. But they're definitely, yes, there's planning in there and breaking a problem down and coming up with a way to approach it. That kind of thing's already happening all over the place. The real question is, which domains does it end up being good at and when, and how fast is all that moving? And what you can do in real time. I mean, if you look at the self-driving car space, that's a real-time safety critical thing, which you've got to respond fast enough to turn the steering wheel or operate the brakes or the accelerator. So those things are, but they're modeling everything around the car, what's going on in the environment, what's happening, where you're trying to go, what's that blob I can see in the distance? Is it something at the side of the road, or is it a thing coming at me? That all those kinds of things are happening in different domains around AI, and we're getting some cross-fertilization between the more robotics AI, which is real-time, and the more LLM AI that's able to have more emergent behaviors and ability to sort of think in ways that are more human-like.
So agentic is really one walk away from this conversation as one of those innovations that's coming on the heels of GPT and adding net new capability. Chris, you were going to say something about optical.
Yeah, so there's a couple of topics that we've touched on that arguably converge in the optical arena. One is thermal management, and the other is quantum. There are folks who have been pursuing optical-based computation for some time, and it appears that there are very strong similarities between that and what people are doing with more traditional electronics in the quantum arena. So maybe you want to chat a little bit about some of the conversations we had with those folks, Shaheen.
Let's do. So optical technology is pretty standard in telecommunications, but when it comes inside the data center, it hasn't quite panned out in a big way. So there's a lot of effort to bring silicon photonics and optical interconnects and even optical computation into the data center. And we had some conversation with AR Labs and Light Solver and Light Matter. So those were some of the presents that we saw at SC24 that we can talk about.
In an earlier life, I spent some time at a company that was trying to create an optical interconnect using broadcast light. So I was very fascinated by the progress that the folks at Light Matter have made. They're actually stacking optical media on top of each other, and they're going after the interconnect space. So I'm actually looking forward to further conversations with them because I want to learn more about what kinds of challenges they see. If we solve moving data at the speed of light, then we've shifted the bottleneck, right? So how practical does that end up being? But I was just fascinated. And they're looking at a wafer scale size for their interconnect. And they're looking to team up with the NVIDIAs and the Intels and so forth of the world to actually bring their products to market. Very fascinating technology.
Yeah, there's also optical at the UCIe level right on the chip that people are working on. Yeah. So it's coming. And I think like many of these advanced technologies, they go through a period when they're permanently 10 years out and then permanently 5 years out.
Right.
I think it's looking like not a very long distance out. It looked really real to me. The pieces are coming together. And famously, Pat Gelsinger, the CEO of Intel, demoed their silicon photonics on stage. I think it was a couple of years ago. So it is coming. And I think when it does, it promises higher bandwidth, lower latency, lower heat, lower cost, higher life, all of those benefits. So a lot of people are watching it.
Right.
I liked what I saw at AR Labs, and it was good to catch up with them. And Light Solver is trying to use photonics for actual computation, not just for communication.
Right.
And that looked really novel as well. And they look like they can do partial differential equations in sort of an analog way.
Delving into a little bit the similarities to quantum computing, where you are changing the state of a photon to reflect the progress in the calculation. And maybe it's because I would need to learn more, but what struck me was how very narrowly defined the problem has to be in order to be addressed by their solution.
I think these systems are best when they address a killer app and they solve it and it can go big. Mm-hmm. But they mentioned some of the language that is also seen in quantum computing. Of course, they don't do entanglement and superposition, but the language sounded very similar. I think it has uses in high dimensional computation as well as maybe security area. So we'll watch them, and it was nice to get a briefing from them.
Yeah.
I want to mention OpenMP. OpenMP has been a standard for programming and directive-based programming in HPC land, and the latest version of OpenMP has a couple of features that I wanted to point out. One is the concept of free agent threads. So they have a pool of threads sitting on the side that can be used for anything that the application needs, and they can spawn their own threads, which is really quite nice. And then the other one was better array syntax and memory management for C++ and Fortran that also looked really interesting.
Yeah, on the software side, with the transition from a lot of small GPU nodes, you've got a large cluster, but each node in the cluster is relatively small. It has a small number of GPUs on it with a InfiniBand typically based interconnect. The Grace Hopper and Blackwell architecture NVIDIA systems are more shared memory. So the size of the node is increasing a lot to be effectively half of an NVL, or half or a full rack of the NVL72. They call it NVL36, I guess, is a half rack, but configured as a single shared memory system with tens of GPUs on it and tens of terabytes of memory. So that architecturally is an interesting transition that's going on right now. And the question is, how do you program that? And part of the answer came during one of the announcements at SC24 from NVIDIA was a new library called CuPy-Numeric, which is basically a API compatible with NumPy, which is the de facto standard mathematrix library. But what it does is that it basically under the hood distributes across many more GPUs in a large shared memory system and also across nodes as well in a cluster. So they're trying to make it easier to come up with ways to take your codes that you've written on a small number of GPUs and scale those out to a much larger scale system.
Excellent. That is up the alley with the other interconnect systems, from Ethernet to Ultra Ethernet Consortium to PCIe to InfiniBand to NVLink to CXL to UCIe. Anything else we want to mention on that spectrum?
We're seeing PCIe every few years. They announce the next version, which is twice as fast as the old version. And many years later, whatever the version is finally turns up in a CPU chip, or the chip architecture starts to catch up with it. So they seem to be delivering on that. PCIe 5 is in the current generation CPUs that you can get. PCIe 6 is an interesting sort of, actually changes the architecture to be more packet-based. You're sending around clumps of data, and that's really what CXL is based off of as well. Or maybe that's the 4 to 5 transition. But there's this transition from being, I'm just sending around cache lines effectively to sending around several hundred byte flits, I think they're called. And then the other thing is the bit rate, being able to cram more and more data down lines by having 4 levels on each wire. So instead of on-off on like a normal sort of digital circuit, they're doing 4-level encoding and a bunch of other tricks to get more and more throughput. So they keep coming up with new tricks and figuring out how to get them to work within a rack. Typically, these are sort of 1 meter to 2 meter distance over copper kind of systems for PCIe. So they're off building that, and they're gradually adding more functionality. And CXL has leveraged PCIe. And there's a little bit of sort of conflict between the groups. If you talk to the two groups back to back, you get quite a different story. They're not completely coordinated in the way they're operating. And it's sort of interesting to see they're each coming at the problem from a different space. But think of CXL as leveraging PCIe as a transport, but putting a more complex set of protocols on top that give you memory sharing, and in the The 3.1, which was announced last year at SC23, is basically a fabric with security and dynamic fabric creation. So you'd be able to have a cluster of machines, shared memory cluster, dynamically reconfiguring itself ultimately. And that's more of a 2-year rollout. So we're not seeing the chips yet. But I didn't see any announcements from the CXL consortium at this year's SC. There's more just like deliveries of CXL 2.0 memory board, memory level things. And this is basically a memory hierarchy where you've got high bandwidth memory directly connected to the GPUs. You've got regular DRAM connected to the CPUs. And you've got CXL-based memory as a big pool that's connected to multiple systems. So you can allocate a larger pool of memory without going all the way to something that looks more like a disk, or NVMe is sort of like the fourth layer in there. So that's kind of where it fits in the hierarchy. Any other thoughts on CXL?
Yeah, we spent a bunch of time in their booth, and memory expansion, like you said, was there. There were a couple of companies doing that, including Micron, that had a CXL compatible SSD kind of a device, and another company that had a whole rack full of memory that could be accessed through CXL. I think the way you described it is a good way to think of CXL, that they're using PCIe as a way of accelerating their path to market, but it really is a different thing.
Yeah.
They're using the PCIe technology with their own protocol.
Then the other thing really is NVIDIA's NVLink, which is doing today what a bunch of things in CXL are promising to do in the future. It's much higher bandwidth. It's aggregating together many more pins on the chips. It's already providing shared memory systems in things like the NVL72. That's all 1.8 terabit NVLinks between the nodes. So that's a lot of pins to generate that, whereas CXL is using 16 pins, I think, for NVLink. That's it's either 48 or 64. Anyway, it's a lot more pins, and they're running at much higher data rates. So in some sense, we've got the industry consortium standards body moving slowly with CXL, and we've got NVIDIA solving a lot of the same problems, but on their own going much faster. And the question is really whether the consortium eventually ends up with something that's useful, or whether it's permanently in catch-up mode and never really gets to a significant sales volume versus NVIDIA, which is clearly right now one of are they? I forget where they are. Are they the most valuable company in the world this week, or is it? They're somewhere in the top 2 or 3, right?
Yeah, they're right up there. Yes.
Yeah, it depends what week you look at it, whether they're bigger than Apple or not. But that's the level of investment that NVIDIA has available to it, because they're growing so fast, they're making so much profit, they've got so much cash in the bank. They are able to invest at a level which is creating an interesting differentiation all on its own. So it's going to be interesting to see what NVIDIA comes up with at GDC next March, I guess, and through into next year, into SC25. And the other sort of larger players, the cloud providers, they generally announce things at separate places. In particular, AWS's big announcements will be the week after Thanksgiving rather than SC, which is 2 weeks before. So really only 2 or 3 weeks after SC is the big AWS conference, where we expect to see whatever they're doing in HPC being announced, but it's a little too early, right? As we're recording this, that hasn't happened.
Right now. Of course, there is also the Ultra Accelerator Link Alliance that is aiming to essentially compete with NVLink specifically.
Yep.
Probably will bear fruit in a few years as well, but it's like sufficiently out there that if you want to play, NVLink is the only choice right now.
Yeah, and that's really why NVIDIA had to develop their own chips with Grace, their own CPUs, right? So they could put NVLink on the CPU. And you've got AMD, Intel, and other CPU vendors need something else that they can put on their CPUs. And the CPU development time cycles are multiple years. So everything starts taking years when you look at, well, the CPU chip has to do this support this properly directly. You can't glue it on, because gluing it on would add far too much latency. When you're looking at a very high bandwidth, coherent memory interface, it has to be directly supported on the CPU chips.
Yeah, I remember Oracle added InfiniBand to Spark on the chip itself, when that was the fastest thing that's available. This is a good segue into what I call NVIDIA and NVIDIA discussion. That NVIDIA is doing such a great job building everything, and all the components are essentially best in class, but they also disaggregate it. And I think they've got a really good, effective story that says, hey, we build the whole thing, but then we disaggregate it, and you can use as much or as little of it as you'd like. which has the cake and eats it too. You have the monolithic thing, but you also have best-in-class integration. But as it relates to interconnects, we've already talked about the spectrum. When it comes to the GPUs that are really the driving force, you also have a pretty wide spectrum. Let's talk a little bit about that.
So NVIDIA last March announced Blackwell, which has just started shipping and will be out shipping, I think, in volume in the new year. Then there's various leapfrog announcements for things which are maybe slightly higher spec but aren't shipping yet. What's the numbers for AMD?
MI300X and A, and then they also alluded to MI350.
Yeah, and there's also allusions to whatever it is that comes after Blackwell. They've started talking about it, but there's basically a speed bump on Blackwell and then another architecture. But the problem with Blackwell, it's already twice as big as you can make the biggest chip. It's reticle limited, right? It's the largest chip that they can lay out, and then you get two of them and glue them together with this chiplet interconnect. So to go beyond that, we're looking at the next generation TSMC process to get you more density, and maybe starting to put, I don't know, how many GPUs can you get on a chiplet? Maybe the next step would be to put 4 of them in a square rather than 2 side by side. But and then we'd be into sort of 1200 watts for the module. It would be whatever, 2 or 3 kilowatts, something like that.
NVIDIA switched to an annual cycle for their chips rather than every other year, which is really quite ambitious. And you said it well, Adrian, that it will cause indigestion for the enterprise, and it'll probably be just fine for the cloud guys that have a conveyor belt of new tech coming in, including their own GPUs.
Well, if you're Facebook or one of the big cloud providers, you can consume these things. No, you just give me more, it's fine. But if you're a random enterprise that just wants to buy some AI hardware, you buy it, you order it, it's obsolete before it's delivered. And by the time you've been running it for 6 months, no one wants to use it because the next thing that has already come out that is vastly better. So the pace of change is too high, I think, for enterprises that are used to buying hardware and getting 3 to 5 years useful life out of it as they depreciate it. You have to think about depreciating AI-based hardware on a much faster timescale, which makes it even more expensive. And the fashion level of what is useful and what do people want to run the latest algorithms on and the rate at which the software is changing, all of those things are giving the more typical enterprise market a lot of indigestion as they try to consume the whole world of AI.
Right.
If they try and do it themselves, I think that what they're finding is that what works is to go to one of the other big vendors and consume whatever they've got, right? Just, OpenAI's APIs are expensive, but you don't get the indigestion of trying to do it yourself, even though you could probably do it cheaper at some point in time.
Now, NVIDIA makes the point that in a post-Moore's Law world that we live in, obsolescence is not what it used to be.
Yeah.
So they try to make a case that these chips don't go obsolete. Just buy the one that works for you, and it can carry on making you happy for a very long time. I'm not sure everybody has quite, got on the same wavelength there. It may be true. In some ways, it probably is. But everybody wants the latest, greatest, don't they?
As you get a year or two into the future, it becomes not worth the power of turning these things on. The power consumption of the old chips for the performance you're getting becomes uninteresting. It's hard enough to make them work at scale already. The software's a bit flaky, the hardware's a bit flaky at scale. When you've got 10,000 GPUs doing something,
right,
your failure rate is actually the limiting factor. They're checkpointing the entire AI workloads about every 15 minutes, I heard.
Yeah.
Because otherwise you'll lose everything because it crashes and you have to restart it. So the older the old hardware is going to get more and more flaky. So there's a couple of reasons why I don't buy the argument that old GPUs are useful.
But they are on an annual cycle. The next generation one is called Rubin, named after Vera Rubin, a U.S. astronomer.
Oh, yeah.
And they carry on with that model. So we'll see what they do at GTC in March. In all likelihood, they will have yet another follow-on to Rubin that they will pre-announce for the following year. But if you kind of rattle them off as a list, you obviously have NVIDIA, that is the 800-pound gorilla. AMD is coming very fast, and their MI300 is doing well. MI350 was mentioned. Intel, one of these days, is going to get its mojo back. The Gaudi 2 and Gaudi 3 chips are getting really good marks. And they also announced the follow-on to Falcon Shores called Jaguar Shores Accelerator. This is when their GPU and AI chips merge. And then you get the cloud guys, Google, AWS, Microsoft, that do their own.
Yeah, AWS has their own GPU architectures called Trainium and Inferentia. They just announced a big deal with Anthropic to run on those. Google have their own ARM-based silicon that's now GA that they said was about 10% higher performance than Graviton 4, which is the latest AWS chip. So we're seeing the ARM-based chip vendors holding a pretty good performance delta. They're managing to get things out more quickly and get to market to, I think, probably hold currently a reasonable advantage over Intel and AMD, or it's possibly AMD are up there still. But the various CPU chips are all sort of jockeying for position, and every year we're getting faster chips, which makes life good from that point of view, as long as you haven't got a data center full of the old ones, I guess.
Right on. So notably, the big cloud guys are doing their own CPU and their own GPU, in addition to outfitting their data centers with Intel, AMD, NVIDIA, etc. So that's kind of really interesting. So Google has their TPU, AWS, as you mentioned, Microsoft does. And then you get the next level, which is Cerebras, Grok, Samba Nova, etc. And then you get others. And most notably among those, I would say, are the neuromorphic chips. Intel has one called Loihi. IBM has one called True North. And then you get Spinnaker from University of Manchester. And then BrainScale is a company that does neuromorphic. BrainChip does one called Akida. And then Rain is a company in Silicon Valley that does neuromorphic and is funded by Sam Altman of OpenAI fame. So there's a whole lot coming in that world that is trying to reduce the power consumption.
And then the other chip architecture we haven't mentioned is RISC-V, which is not that visible to people, but it is actually on every NVIDIA chip. So the local microcontroller, if you like, the firmware that runs GPU is actually running on RISC-V chips on the NVIDIA system. So it's quite an interesting rollout. And we may start seeing more RISC-V based mainstream architectures rolling out as a software target. I did a blog post on this after going to the RISC-V summit with Shaheen a few weeks ago. I also did a blog post on the NVIDIA benchmarks, trying to analyze and understand exactly what was going on with their claims that they were making last March. And both of those on my Medium.
Yeah, I saw those both highly rated and a lot of traffic there. Barcelona Supercomputer Center mentioned that they continue to be interested in driving RISC-V, and I expect that RISC-V in Europe will happen in the HPC world. There were several companies that announced really high-end chips at the RISC-V conference that we were at in Santa Clara. So it's coming, as you mentioned. Well, this was a nice, good whirlwind review of SC24. Anything we haven't mentioned before we wrap?
I did want to note that, we spent a little bit of time talking about the top 500 systems, but the number one system, El Cap, is actually number 18 on the Green 500, which is something worth noting, that we don't necessarily get huge energy consumption, maybe overall, but huge energy efficiency we get with some of these large systems. I think that trend was something that we want to keep an eye on.
I think that's where the cloud guys can teach a few things.
There's certainly some efficiencies in scale and the design level. I think the most efficient data centers out there right now are the hyperscaler ones. And they've moved on from making them power efficient, building their own backup generator technology, their own construction standards, right? There are low carbon concrete going into these things and a whole bunch of things. So they're optimizing the whole space for sustainability, cost, and scale. It's pretty hard to compete with that unless you're operating at that scale. And I think it's probably only, I'd say Facebook are the non-cloud cloud, if you like. They're operating at huge scale with a similar level of technology, but there are very few people operating at that level. Also, water usage, talking a lot about cooling. There's a lot of work right now on water usage efficiency and replenishment to make sure that the water coming into the data center is replenished as clean water, even if what's coming in is non-potable water or water that's contaminated in some way. They want to process it so the water that comes out can at least be used for irrigation or can be fed off into drinking water effectively. There's a lot going on there, and the latest data centers are being built with that kind of stuff in mind. So typically, if you see deployments in old data centers, there'll be fairly bad power usage and water usage efficiency or effectiveness. And then the very latest builds are really pushing the boundaries of what it takes to be extremely efficient on both power, energy, sustainability, water usage, all those things. And the latest trend seems to be building nuclear power stations or attaching your data centers to nuclear power stations. So we're starting to get a little bit more People looking for how do we generate base load with nuclear, where we've got cheap solar, we've got cheap wind, we've got cheap batteries, but to really flesh out and give them more options, they're doing large investments in nuclear. That's an interesting trend really in the last 6 months to a year. We've been hearing more about that. It doesn't mean they're not doing other things, they're just doing it as well as.
That's right. I see a whole emerging area that some people have called infratech that includes power sources, transmission, data centers, modular data centers, etc.
Yeah, Google's doing a little bit of geothermal as well. So that's the other one to watch, because geothermal, there's lots of hot rocks if you dig a deep enough hole.
That's right. Well, that is a wonderful source if you can get it going. And there were a few people at SC shows a few years ago focused on geothermal.
Yeah, and the only fusion reactor that works is 93 million miles away and is on all the time.
We'll use it every day. All right. Well, on that note, let's wrap up this episode. Thank you, everybody, for listening. This is a super long episode, but hopefully you saw value in it. Thank you, Chris. Thank you, Adrian.
Cheers. That was fun.
Oh, it was fun.
All right. Take care.
Okay, bye now.
That's it for this episode of the OrionX Download Podcast. Every episode is posted to orionx.net and shared on social media. Use the comment section or tweet us with any questions or proposed topics of discussion. If you like the show, rate, review, and share it. The OrionX Download Podcast is a production of OrionX. Thank you for listening.